All right, let's look at part B of example 4.22. We have, just like in the previous one, we have a solid rod that has been bent into the shape of a crank. For part B, we want to locate the point of the highest combined torsional and transverse shear stress and draw the representative volume element. Right, remember the formula for a torsional or shear stress due to torsion is 16T by pi d cubed. So basically we want to look at the point where the torque is going to be the highest, or this twisting moments. Let's kind of do it by inspection. If we look at the first point, we have this 1,000 Newton load, right? There's no twisting about the solid round bar in this point, so actually we have no shear stresses right there. If we, for example, just look at this part over here. So next, let's section somewhere over here. Right now we have this crank, there is some distance, so we have the capability of producing some twisting, right? The force is 1,000, the distance or the moment arm would be 100 millimeters. We got some twisting there. Now let's check the last point over here. So we have the force and now we're off a distance of 250 millimeters, and now the twisting would be in this direction, right? So because that distance is the highest, means we're gonna have the highest twisting stress. I'm sorry. The highest shear stress due to the torsional loading. Anyways, so let's transfer this load over here. Again, I want to remind you, you could section over here and figure out the internal forces and moments to make this be in equilibrium. And you'll see that those forces and moments that you get should be completely the same magnitude. Same magnitude, but opposite direction of what I'm trying to get over here. So my shortcut is, instead of figuring out the reaction forces over here, I'm just going to calculate the resultant force and couple moment at this point due to this force, right? So the resultant force is just going to be, well, force in the same direction, 1,000 newtons. And what it can do, right, is 1,000 Newton force can create a twisting motion, right, like so. The force is going to be, so here a force down, like so. This force is going to be 1,000 newtons, and the distance from the force to this point is 200 plus 100, or 300 millimeters, right? And so we get here 300,000 Newton millimeters. When we look at this one, this bending about, let's name the axis again. We'll call this one X, Y, and Z. This moment about the Y would be a bending, right? So this is a bending moment. We'll just call it an M. Or we can specify MY is going to result in bending. And finally, we have this 1,000 Newton force, right? It doesn't pass through the Z-axis, right? So there is some distance, so it can generate some twisting, which is how we got to that point, right? So we have some twisting in this direction. It wants to twist down. That's going to be the twisting, right? It's going to be a torsion, or a torque of 100 times the distance, which is 250, or 250,000 Newton times millimeter. And that's it. So again, you could cut over here, look at the front part, figure out the reaction, internal reaction forces over here. They're going to be equal and opposite to what I have over here. Okay, so next we want to locate the point of the highest combined torsional and transverse shear stresses. So remember, we have these two cases. So first, let me color this section, which is where we made the cut, right? And then I'm going to draw that circle, again, that cross section, and I'm going to draw it again. I'm going to draw it 2 times. So in one, we'll remember what the torsion is doing, right? So this is this guy. And at the other one, we're going to look at the transverse shear, what it's doing. Because what we want to look is, we want to find the point of the highest combined. Okay, so we know a torque is going to be maximum right at the outer fibers of a solid round bar, right? What is the direction going to be? Well, it depends on what points we're looking at. Usually we look at the top, bottom, left and right, or these points that are kind of aligned with these axes over here. So what is this torque over here that looks like this? What's it doing at those specific points? Right at the top is trying to shear it like so. At the right hand side is trying to do this, bottom, and the top. Basically, I just took this circle in the same direction, right? And I'm just looking at the tangents. When I look at the transverse shear, right? The transverse shear is from the top bottom. So the arrows are pointing down like so, right? You should already know from solids that if we look at the very top and the bottom point for a transverse shear, this is going to be a 0. We cannot generate there, but it's going to be maximum over here, these axes over here. So this is going to be the max. What direction is it going to be? Well, it's going to be the same direction as the arrow. So here we have something down like so. And on this one, we have an arrow pointing down. What is the value? You have the general formula from the solids, but remember, in this class, we use a shortcut, which makes our life easier. So the maximum transverse shear for solid round bar is 4B divided by 3A. So this value is going to be 4V by 3A. And this shear stress, remember, it's already this one over here, 16T by pi d cubed. So we want the point where the highest combined torsional and transverse shear stresses are. Let's look at the top. So at the top, we got torsion, but no transverse shear, right? So that's not a good point because we only have contribution of 1. If we look at this right point, we have a contribution from the torsion pushing down and the transverse. So in this case, we have these two and they're adding together, right? So combine the two because they have the same direction they're going to add. So right now, this one is looking like a very interesting point right now. If we look at the bottom, at the point at the bottom, we have some shear stress from the torsion, but nothing from the transverse, right? So that's going to be a lower value. And then if we look at this point here on the left, we have contributions from the torsion and from the transverse, but they're in opposite directions, right? So they're fighting each other. They're going to counteract and they're going to end up lowering the shear stress at those points. So instead, what we have, right, we just found the point where we have the maximum combined torsion and transverse, which is this point over here, which if I draw it on this original one, we'll put it over here. I know it looks a little bit different, but it's because this is like a 3D and this is like a 2D. So we're looking at this point and we're gonna, essentially they want us to draw the volume representative element. So we're actually gonna cut a little cube in there like so, down and something like that, and that's what we're going to draw. Remember, we still have a bending. We still have bending over here. But if I look at the round cross section, right, and I have a bending stress that does something like this, it's going to be putting the top portion in tension and it's going to be compressing the bottom. And this point over here just so happens to be right at the neutral axis where for the bending, this is for bending, where sigma for bending here is 0. So we don't have to worry about the bending right now. So let me go ahead and blow up this volume representative element. Again, we're looking at it like this. So it's looking something like this. Again, I'm trying to capture that curvature of the solid round bar. Here's our letter A over here. And we're probably cutting somewhere something like what's supposed to be a cube, sorry. Right, that's that volume element. But remember, where we made the cut, we're exposing the left-hand side, this face over here. So this is what we're exposing, which means that's where the loading is going to be applied. Right? So what do we have? Let's look at the one for the torsion first. So we have a down, in this case, a downward arrow. So we have an arrow pointing down. This is going to be from torsion. The formula is 16T divided by pi d cubed, which when we substitute the values is 16 the torsion was 250,000 newtons times millimeter. Again, divided by pi times the diameter, which is 25 millimeters cube. This is the same value as last time, but I'm gonna double punch it in the calculator just to make sure I don't make a mistake. So 16 times 250, 1, 2, 3, divided by pi times 25 cube. It's 81.5. What are the units? Again, Newton per millimeter squared, which is the same thing as a megapascal. So 81.5 megapascal. Again, this is from torsion. Torsion. This one here. And remember, we have the arrow pointing down for the transverse shear. So if I were to draw here, let's put it over here in the top. Torsion is this guy. And if we now do transverse shear, right, we have our little volume element again. This is A. That's the phase that we're looking at. And then we look at the direction of this arrow, right? This transverse shear is passing straight down, which means right on this phase, we have an arrow going down like that. The value is, for that transverse shear stress, is 4 times the shear divided by 3 times the area. Just put it here at the bottom. So it's 4 times 1,000 divided by 3 times the area. Well, the area of a circle, when they give us a diameter, is pi by 4 times the diameter, 25 millimeter squared. Whatever comes out of here, right, is going to have units of newtons divided by millimeters squared, right? So it's going to be a value of megapascals. Let's see what that value is going to be. So 4 times 1,000 divided by 3 times pi by 4 times 25 millimeters squared. It's going to be a very low value. The transverse shear values, or transverse shear stresses, are always very small. Look, 2.71, 2.72, 2.72 megapascals. In any case, the direction of the two are the same, right? That's why we picked this point already. So these are going to combine. And so the final stress element, right, is going to look something like this. We're going to add these two together. So if we look at the 3D, one is going to look something like this. It's a little, doesn't look like a cube, but we have something like this. So remember, that's the arrow. And combine already for the two would be 81.5 plus 2.72, or 84.22. So 84.22. Look at the direction of the arrow, right? So that means I need one and the opposite on the other side. And then I need to counteract this moment with an arrow pointing that way and an arrow pointing that way. In this case, because we have no normal, we got nothing pushing on it, so we have nothing stretching, the bending moment is 0. So that's all we have, just a combined shear. If we draw it as a 2D representation, right? So I'm going to look at this one from the front, which is in this direction. Sorry, let me use a pen. I'm going to look at in this direction. Again, the cut was here towards the left. So this is where we had made that cut. That arrow is pointing down. So it means this one points up. That one points that way, and this one points that way. Let's look at the direction of the axes. If we're over here, this line here with the bottom is the X. So this direction is the X axis. This is X axis. And up and down is going to be the Z. So this is the Z axis. So specifically, this arrow is on the X face of the cube and is pointing towards the z-axis, this, like, to be like completely thorough, would be a tau xz value, and this would be 84. Oops, 84. Sorry, I got ahead of myself with that decimal point. 22 megapascal. This would be a positive tau xz, because that's the arrow that is on the x phase and pointing towards the z. If these arrows were reversed, like pointing down, this one pointing up, then it would be considered a negative, but as it is, it would be considered, now it's a positive. Again, for this homework, I don't want you to worry about putting in positive or negative, just the absolute value. Basically, you put in a positive number, but the important thing that I want you to realize from the homework is these two are going to combine at a specific point where they're going to add together, and this is going to give us the highest combined torsional and transverse shear stress. So I think we're done with this one. Let me just read the problem again just to make sure I covered everything. Maximum torsional and transverse shear stress. We have the volume element here in the volume and the 2D. I think that's our answer. Again, they're added. And I think that's it.